Okay, very good. So let's start just by summarizing what we saw in the morning. So the first thing I reminded you was that there is a set of numbers which are called the CFT data, in terms of which you can build up more complicated objects, such as correlation functions, non-trivial correlation functions, say 4 operators. And what is this CFT data? It's a set of OP structure constants that tell you how two operators produce some state, and then another structure constant that tells you how the operator is annihilated at the top. So very much the analog of the pentagons that you saw in Benjamin's lecture, where you had some pentagon for some transitions that propagate from the bottom to the top in this polygon business, right? And then we have deltas, which govern the propagation. Here they are encapsulated in some conformal blocks. In Benjamin's case, the energies appear just e to the minus energy times tau. So e to the minus energy times tau. Here we can resum many of the states together in a conformal block, but each conformal block starts with e to the minus energy times tau, if you want, using the same kind of variable. So this is the analog of that propagation of states with a given energy and a given spin. And so the goal is to find this CFT data. Of course, one should say that it is not granted that this is the best way for computing, say, 4-point functions. By no means, we don't know. It's not obvious. You might say that normally it is not the way people compute 4-point functions, by studying 3-point functions and putting them together. In the case of amplitudes, for example, for the Wilson loops, it did work very nicely. That we had pentagons, it seems up to now to be the best way for computing amplitudes in n equals 4 at finite coupling. So here it's also a long shot. Maybe in the end we will learn some things, but we will rethink about how to compute this from scratch. So again, but the point is that we have these probabilities of creating and annihilating the state at the bottom and the top, this being the bottom, this being the top. And we have this f, which is a conformal block, which is just some fixed function, which is fixed by conformal symmetry, and z bar are the cross ratios. So how do we start studying this data? So we saw that the spectrum, say for these SL2 operators made out of derivatives and one complex scalar, they are given by solving some Bethe equations that you think of as describing the scattering of the derivatives in the lattice made out of the Cs. Okay? So the picture is that you can associate to each operator a spin chain like this, where you just think of the trace where the derivatives are. You think of it as a cat which tells you where the positions are. Then this is a spin chain. The dilatation operator will be a local Hamiltonian by planarity, and you have to find this wave function by diagonalizing, by solving the problem that Hamiltonian acting on wave function is equal to the dimension times wave function, and the Hamiltonian is here. And we saw on an example on Mathematica the connection between these two expressions on an example. We saw that the spectrum of all operators of length 4 and spin 6, we computed this by diagonalizing by brute force this matrix. And on the other hand, we solved these Bethe equations for L equals 4 and spin 6 and found exactly the same numbers. How would we make the connection between the two analytically, or closer? So this goes through, of course, the way these two talk to each other is through the so-called coordinate or algebra, through some Bethe ansatz. The point is that the wave functions that diagonalize this Hamiltonian are of Bethe ansatz form. So this is an ansatz, where you write a sum of plane waves. So this phi 1, 2, 3 is like a plane wave P1 N1, P2 N2, P3 N3, three particles moving. You will draw it like this. And here it's P2 N1, P1 N2, it's like 1 and 2 exchange their momenta. And here the second two exchange the momenta. And now these two I never know. One, these two. So this is like this. And this is like this. And this, the three scatter. And the weight of each of these plane waves is an S matrix, say here, particle 1 and 2 scatter with each other, and we get S12, where this S12 is just the S matrix between particle with momenta P1 and P2, and U's are just the rapidities that parameterize the moment. Okay? So this turns out to be the wave function that diagonalize the Hamiltonian. So what I'm going to do now, for example, just to conclude with this Mathematica part, is let's plug this wave function act with it on the Hamiltonian and check that it does diagonalize. So this would be really using the Hamiltonian, but also using the Bethe ansatz, really establishing kind of an analytic connection between the two. And then the Bethe equations there just follow from imposing that this wave function is periodic. You impose that this wave function is periodic, you shift n1 by n1 plus L, you compare exponentials, and you read off these Bethe equations here, which have the meaning of periodicity. This you saw in coordinate Bethe ansatz lectures by Core, right? Very good. So, let me take this opportunity to mention that, of course, this is only valid at one loop. What happens at higher loops? So at one loop, the interactions are ultra-local, and everything I'm saying here is correct. But at higher loops, as you go to 2 loops and higher, you have to start correcting this wave function. So let me tell you what happens at 2 loops. So that is the 2-loop Hamiltonian, so the wave function gets 1 loop corrections. It's like the generate perturbation theory. When I say 1 loop, the wave function has 3 levels, it's always shifted by 1. And what happens is that this wave function gets corrected, and there is 1 plus g squared times some delta ABC. And this delta ABC is what we call contact terms. So what is happening here? What's happening is that the particles plus dot 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 for higher loops. What is happening is that as the particles are moving on this lattice, they move, and then they scatter, and there is, if you want, some explosion region, which has to do with the range of the interaction. But as the range gets bigger and bigger, as you go to higher and higher loops, you have to start enlarging the region that is the range of the interaction, and you can only trust this wave function out if the particles are separated enough. So what happens is that this delta ABC is non-zero only for the cases where, say, the derivatives are very close to each other. Okay? So what would this delta ABC be? So this delta ABC, which is a function of PA, PB, and PC. As we said, it's 0 if all of them are well separated. N1, N2, N3, well separated. But then, for example, there will be a contact term if 2 of them are close together, of PA, PB, if N1 is equal to N2 minus 1, and N3 is far away. Far away just means more separated than 2 units. And, or it could be the last 2 that would be close to each other, of PB, PC, if N1 is far away, but N2 is equal to N3 minus 1. And then, or, for example, another case, they could be on top of each other, 2 of them, and 1 of them close to it, of PA, PB, PC, if N1 is equal to N2, which is equal to N3 minus 1, etc. Okay? And as you go to higher loops, you would also start to take into account the case where they are not together really close to each other, but separated only by 1 unit, and so on. And the point is that while we have this coordinate Bethe ansatz description here, it starts to be modified at higher loops. These contact terms start to be messier and messier, and we don't have a systematic description of them. So we don't know, for example, what these contact terms are. Okay?
I don't know if all 4 5 1 loop.
No. No. Even for the first ones, we don't know. So again, to find this, what you have to do is diagonalize, find the solution to the problem, Hamiltonian times psi equal energy times psi, where for the Hamiltonian, now you keep g squared plus g to the 4. You keep the nearest neighbor and the next to nearest neighbor interaction. And solving this problem, this Hamiltonian is known, it was computed by Zwibble, but it's kind of a mess to work with. It's kind of very messy to work with. You can work with it up to, say, 4 particles or 3 particles. You can program it in Mathematica, it's painful. And you can compute a little bit these contact terms. And you do find something kind of interesting. You find that actually this contact term, for example, you find that the contact terms are not as complicated as they could be. Namely, this one is equal to 0, this one is equal to 0, this one is just equal to a contribution from the fact that there are two that are on top of each other. And only the contact terms where derivatives are on top of each other and not when they are neighbors are non-zero. Okay? It just turns out that you have this ultra-local property. In this case, you only need this one and the one where the three are on top of each other. Okay? So there is an experimental ultra-locality at two loops. But we don't know why. Okay? A priori, more terms could be non-zero, but it turns out that only this contact term and the one where all of them are on top of each other are needed, and so on. As you go to 4 loops, to 4 particles, it seems that you only need a contact term where 2, 3, or 4 particles are on top of each other, and they factorize, they follow the same pattern.
So there is another form of this.
Exactly. So then let me mention it since you asked. So in fact, the Hamiltonian is not something totally well defined, because you can always change your bases. You can always rotate your cats, and it changes. What is physical are properties like what's the spectrum. The spectrum is physical, but the Hamiltonian itself is not. And indeed, there are 2 Hamiltonians in the literature, one by Eden and Staudacher, and one by Zweibel. The one by Zweibel is the one I mentioned because it's the only one that allows for any number of derivatives. By Eden and Staudacher, they consider up to 3 derivatives. So it's not the most general one. And indeed, we found out that they are related by a change of basis. And for example, if you use the one by Eden and Staudacher, these guys are not 0. They become 0 after you rotate. It's the nice basis, this Zweibel basis is the one where the contact terms get this experimental ultra-locality. So we are going to use this ultra-locality in the last lecture. For now, it's kind of an experimental fact. And to reinforce the point, what I want to say is that there is no algebraic description. It's not like we have an option between coordinate and algebraic with ansatz, because algebraic is nicer and more elegant and less synthesis and so on. It would be great, but apart from SU2 sector at the first few loop orders, as soon as you go to SL2 or SU1/1 or other sectors, there is no algebraic description. We don't know of an algebraic description, some R matrix, something, out of which we can construct these states in a systematic way. We just do it to leading order, and then we do perturbation theory and find these messy contact terms order by order. Okay? Very good. But you might be asking at this point, why am I discussing all these wave functions that I just said are not physical? Why am I discussing wave functions if all we cared before was the energy spectrum of the spin chain? And of course the reason is that we only care about the spectrum of the spin chain if we are interested in the spectrum problem. But if we want to study correlation functions, 3-point functions for example, what matters are exactly these wave functions. So it's the problem which is the analog of computing form factors in integrable models, and what matters here are precisely these wave functions. Exactly like in this pentagon approach where we had the spectrum that Ben computed, and then we had the pentagons where the pentagons are really like overlaps of 2 states, like scalar products of 2 flux 2 states. I don't know, Ben, did you do an example at 3 level of compute? No. So, but these pentagons, you have a state in the top, a state at the bottom of the pentagon, and you overlap the 2 states. So here it's pretty much the same thing. So we will have, when you compute the structure constant, what are you doing? You are considering 3 spin chains, 1 spin chain for each of the operators. So let's represent each spin chain by a circle, because it's a trace, it's a ring. And then what you are doing is contracting, uniting these propagators of the constituent field. So if this is a Z, this will be a Z bar, a complex conjugate, and so on. And you would be computing this. And what you need to know are the wave functions of these operators to know where exactly are the excitations, what is the result of doing this with contractions. So it's a very non-local process where you need to know where the excitations are to be able to evaluate and to solve this combinatorial problem. Okay? So is it clear that this is about the wave functions? Because you need to know the wave functions here to contract all these states. Okay? So it is clear that this problem is related, let's be precise a bit later, but let's just say that in the same way as the spectrum was related to the energies of the spin chain, this one, it's clear, even though we are not being precise, it's related to scalar products of spin chain states. We need to study overlaps, we need to know about wave functions. So let me tell you a little bit about the scalar products, forgetting having this as motivation in the back of our mind, but without trying to make a sharp connection, and we'll try to make a sharp connection with the spin chain in the with this problem of three-point function and so on. So what scalar products can we consider? So suppose I take one beta state and another beta state. Can someone tell me what this would be? Two different beta states here. So we take one beta state, something like this, say with 4 particles or 3 particles, and take another one with another set of solutions to Bethe equations. So we take one state, we solve Bethe equations, we plug here, we find one state. Then we find another one with another set of Bethe equations. Then we compute the scalar product between the two. Sorry? 0, because they are both eigenstates of an Hermitian Hamiltonian. So this would be 0. And the interesting one would be, or the simplest one that is non-zero, is just a norm of this beta eigenstate. Okay? Yes.
So this higher Hamiltonians actually denote strictly Hermitian.
Depends. Some changes of bases make it non-Hermitian. This one is Hermitian. Yeah, so it's sometimes. Yeah, because in SL2 what happens is that you have the Hamiltonian is the generator L0, and then you have L minus and L plus, which are the other two operators. And sometimes you like to have L plus be just derivative. You don't want it to be corrected. Then you have to put very asymmetrically all the corrections in L minus. And that's what makes it this kind of non-Hermitian stuff. Zweibel, no, he says that L plus is not just derivative. It's something that gets corrected, L minus also, but the correction is symmetric, and then he distributes the complication through both operators. Okay, very good. So, this side remark, I'm not going to repeat it, it's not important for the lecture. So, and then this is one case that we could compute. So this is a function that depends on the beta roots of the operator. And this is one scalar product. It's called the Godin norm. And let me call it B, or let me call this norm, so with 1/2. This would be B, depends on the length of the operator, and on a set of beta roots. Okay. Another scalar product that turns out to be the one that we need. We only need 2, it so turns out. But the other one that will turn out is the one that we dubbed with called in double vacuum decay, which is a name that we always forget, but we wanted very much to be DVD because we are nerds. And so what is this double vacuum decay? It's the scalar product between a bit ansatz eigenstate and here some state that is not an eigenstate of the Hamiltonian, otherwise it would be 0. And what is it? It's a state where in the first L sides you separate the spin chain in the L sides and L minus L. And in the L minus L sides you put the vacuum. And in the first L sides you put some homogeneous gas of particles. Okay, of S particles. Okay?
What do you mean by homogeneous gas?
By homogeneous, I just mean that I consider something where I have, for example, let's suppose, where I just do this. I sum over n1 smaller or equal than n2, smaller or equal. Let's suppose that S is equal to, let's do an example here, S equal to 2 small l equal to 5. Small l is not enough. S equal to 2. I sum over n1 smaller or equal than n2 smaller or equal than l. Cat n1 and n1 and 2. Okay? This tensor with the vacuum, so nothing on the length L minus L. Okay? And then this stuff here, I multiply this by psi Bethe ansatz equation. Let me put an L to indicate it's a state of length L. Okay? So note that A, when L is equal to L, is equal to what? 0. Why? Because an homogeneous gas of particles, if you put homogeneous gas, is just a descendant. Right? It is just acting with S derivatives on the state. So it is the same as saying Bethe ansatz with vacuum and taking derivative. So it should be 0. So when small l is equal to L, or when small l is equal to 0, this result is 0. But otherwise, this is not an eigenstate of the Hamiltonian. Right? You can easily see you act with the Hamiltonian, and at some point, some derivative will hop from the left part of the box to the right part of the box. Right? You split your state into two regions, and the Hamiltonian will start moving stuff from the left to the right if you act it a long time. It's really like a gas that you put in a corner of the room, it will diffuse to the rest. Okay, so that this one is clear, that this one is important should be obvious, because of course we have to normalize our operator, so it's clear that we will get a bunch of b's in the denominator. Otherwise 3-point functions don't make sense. This one is a bit funnier, it might look a bit weird. This object, this one is B is used already, so we call it A. AL, that depends on the set of Bethe roots. So it so turns out that this A, this we call double vacuum decay amplitude, and this norm, which is called the Godin norm, these are two scalar products. You see, they are well defined. They are two objects that depend on the set of Bethe roots. And it so turns out that they are all we will need to study the problem in these lectures. This, of course, will become clear later on. Okay. So then let me just tell you what these objects are. Okay, and then what we will do is open Mathematica and do 3 checks. First, we will check that the wave function is correct, namely that it diagonalizes the Hamiltonian. Once we check that it is correct, we trust the wave function, we compute these two things and check that they agree with what I'm about to write. Okay? So these are the 3 checks.
Could I ask a question?
Yeah.
At higher loops, do you correct what you mean by homogeneous gas? Or it is always the same combination?
So let me discuss higher loops when I will discuss when I will discuss the connection between these scalar products and the structure constant. Because if I don't mention the connection, it is not clear what you mean by higher loops. So correcting the 3-point function is clear. The 3-point function starts at 3 levels, 1 loop, 2 loops, 3 loops. So that is well defined. Scalar products by themselves are not really well defined, only when put together into something physical. So let's discuss this question when it comes. Ask me again when I discuss the connection with 3-point function. So what are these objects then? How do they look like? So you saw Godin's norm in cross lectures, right? Yes, the norm of a Bethe state. So let me write it down again. BL, that depends on the set of root UI. It's a very nice object. It's a determinant of size of the number of particles. So it's a determinant of a matrix of size S by S. And it's kind of the Jacobian between the change of variables between the momentum P and the mode numbers N. So if I want to use rapidities instead of momenta, then I will have to compensate a little bit. So let me do it with rapidities, and then I will compensate. It's the derivative with respect to uj of the Bethe equation for uk. So L times T of uk plus 1 over I sum over L not equal to k S of uk ul log of S of ul. So this would be the change of variables from odd numbers to use. And as I said, it should be dp, so you have to convert, so you have to divide by the derivative with respect to PA with respect to UA. Yeah, this is just put, if you want to put here PJ instead of UJ, and then it's perfect. What about A? AL of U. So AL of U, the claim is that it is given by the following. So there is a denominator, which is simple. It is 1 over the product over J not equal to K of F of Uj UK times the product over J. There is a square root. Product over J e to the minus I P of Uj minus 1. Where this function f of u and p is 1 plus I over u minus b. So this is the easy part. And then the complicated part sits here upstairs, and it's the following. You should sum over the ways of partitioning this use into two sets, a partition alpha and its conjugate partition alpha bar. So you split u into alpha and alpha bar. And you sum over all ways of doing it. Then you multiply, there is an overall minus here, then you multiply over the roots belonging to alpha bar e to the minus I p of uj times small l. And then there is an interaction between the roots in alpha and the roots in alpha bar f of uj uk. Okay? And to this loop order, Ivan Kostov showed that this is also given by some nice determinant. And I will write a nice determinant. I will show you the nice determinant in Mathematica. Okay? But I want this form here because at loop level, the determinant representations are not that nice, so it's better to keep this form with a sum over the partitions. Yes, sure.
First of all, Ivan has been twice in 2. Is something changed in that also?
Sorry? Can you what are you asking?
Is quantity AL the determinant formula in SU2 is
Yeah, but the determinant formula doesn't. You remember, Ivan derived this for any function here. And SU2 and SL2 is just some sign, so it's the same. Sorry? Yeah, it is just change length to minus. It is some simple analytic continuation. Any question? Yes?
In this last term in the denominator of AL, didn't we have like an equation for in the previous
We had, you mean here?
Yeah.
We had a product of the first term is equal to 1. Without the minus 1. Yes.
Are you missing a square root of the b, or did you change the notation to it like that?
Yeah, I'm missing a square root. More? And here, and I'm also doing something else, I think. I'm not sure, maybe not. We'll see. It's just, this square root looks a bit suspicious. Probably we are taking the absolute value of a because it's all that matters. So let me make just this quick comment that I know I will make it later. I think it's okay actually. Any other questions? So let's go again into Mathematica mode and advance 3 more subsections in Mathematica. Slide, laptop 1. Slide. Okay. It says here that it will work in 50 seconds. So you have 50 seconds to ask any questions that you might have. it working? Perfect. Okay, so let's recap. So, it changed definition. How much time do I have? 25 minutes. Wow. It's much more than I expected. So again, am I going too fast? I'm afraid I have the impression I might be going too fast. Yeah? No? Okay. So let's recapitulate. So we had this nice function that we can ask for the spectrum of some spin and some length, and it gives us the spectrum, 5 states. If we have length 8, spin 8, there are more states, and so on. How many there are? There are 13. We can ask for the Bethe roots, and we are going to use the Bethe roots now. So here is a set of Bethe roots. I remind you that, say, let's do 4, 6, so let's make /n. This is a list of lists. So this is one set of Bethe roots. This is another set of Bethe roots, another set of Bethe roots, another set of Bethe roots. Each of them obeys Bethe equations of length 4, and it has 0 momentum. Very good. Then we had the Hamiltonian, and we did this nice check of checking that if you take the spectrum of states of, say, length 4 and spin 6, removing the ones that are also states of length 4 and spin 5, because this will be a way of removing all the descendants, we get this nice list of 6 numbers, which are perfectly agreeing with the list of 6 numbers that we get from solving Bethe equations. So this is very nice. It checks that the normalizations are good and so on. So let's go now to doing a check which is even more direct. We just take the Bethe equations. So what are we doing here? So let's now open this section. If you're also opening the notebook, you can open this next section. And let's run this. And let's ask what is this psi Bethe, so for, say, 3 particles. And it gives this where we recognize exactly what I wrote there. Phi 1, 2, 3, phi 1, 3, 2 where I exchange S2 and S3, 2, 1, 3 where I exchange 1 and 2, and so on. Yes? It's clear, just a wave function for 3 particles. And if I do 4 particles, how many terms should I have? How many terms should I have?
24.
24, so they have 4 factorial terms, right? And we can indeed ask, and we have 24 terms. So we have all possible permutations. We get this state, for example, with 4 S matrices. We could draw a picture, and so on. So how did we construct this? Let me just show you a little bit, because it's again simple, and since I have lots of time. So we took, say, 4 particles, here it is, and we did permutations, all possible permutations of 4 particles. And this gives 24 elements. See? So then we have these permutations. And then we sum over the permutations. P is now a list. P is this, then it's this, then it's this, and so on. So when P is this, what do I want to do? I want to replace A of this and phi of this. But this is ugly because there are too many brackets. So what you can do is the following. What is this object here? If you ask what is this object, it's a list that contains 1, 3, 2, and 4 as its branches. So you want to replace this, and what is what you would like, which is this. This is what we would like, A, just to be simple. It is the same thing where you have A instead of list. So this can be done by replacing the head of the expression, which is this list, by A. So we do this, and the head becomes A. Okay? So this is all we are doing here. By doing this small piece here, when we put 4 here, what we are doing is having this A, and this is nicer than if we would use just A applied to, phi applied to, where we'll get all these extra brackets. Okay, so that's nothing special, just getting rid of brackets. And now we have an amplitude for each permutation. And what do? We say a permutation, if B and C are not ordered, if B is bigger than C, replaced by A, where C and B are exchanged, you see, C and B are exchanged, and you pay a corresponding S matrix. So now, when you apply this expression, You apply it, say, once, you say replace this, and it does this. Some S matrices appear. And then you want to say apply it another time, 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 apply it once more, and it's not changing anymore. It already ordered everything. Now, instead of doing all this, you can just put 2 slashes, and this is apply it until you are tired, or until there's nothing more to do. So this is much better. And then, once it's applied, now it's always A, 1, 2, 3, 4, because it ordered, so at the end we got this remnant, this A. So then we just say, okay, A goes to 1 at the end. Okay. And this gives the state. Okay? That's just a fast way of generating the wave function. Is it good? And then, for us, what do we have? For us, the momentum, this plane wave, is just a product of u plus I over 2 over u minus I over 2 to the position nj. Because remember, this is e to the ip. So, this is what this phi is, this phi ABC that I wrote there. And the S matrix is this stuff, ui minus uj plus I, ui minus uj minus I. Okay? So now, if we ask what is psi, say 3 particles, here is the wave function. So this wave function depends on n1, n2, and n3, and on the beta roots u1, u2, and u3. Okay? Is it okay? And now we construct a state, multiplying the wave function by the cats and summing over n1, ni, going from ni minus 1 up to the length L. Okay? So all this complication here, all this second line, the first line is clear, right? You have psi, a wave function, and then the cats. Remember this cat stuff, when you have cat, 1, 3, length 10, gives just 1, 1, at position 1 and 3. So the first line is clear. And then there is this mess that if you are not used to, should be total mystery, what this is. And this is just generating, when you have a sum, you have to say sum of, say, psi. Let's do something like this. Or let me use some other capital psi. Psi of, say, n1, n2. And then I want to say n1 goes from 1 to 10, and n2 goes from n1 to 10. And it works. And then I want to do when I have n1, n2, and n3. And I want to do the same thing, and then here n3 goes from n2 up to 10. And now I just want to do it systematically, such that I specify some s, and I generate this stuff here. Okay? So, and what is this stuff? This stuff here, you see, this stuff here, it has no brackets in the beginning or the end. So it's a sequence. This table of ni and n minus 1 is what you will generate. This table is if it had brackets at the end. This removes the brackets, and this tells to evaluate now, because otherwise, if this doesn't look like an iterator, it doesn't look like the limits of the sum. Okay, so this is all there is. So now if I run this, say, I don't know, 4, 2, it gives the state of 2 particles and length 4. So these are the wave functions. And I could try to simplify a little bit. So this would be the wave function. This is a cat. Here you see. This is a cat, and what multiplies the cat is the weight. Okay? And now we can check. So now it's the fun part. We take the Hamiltonian and act on a given state. We get a big mass. Or we take the spectrum. We take this spectrum and take the first element, say, one of the elements of the spectrum. And indeed, if we replace the root UA by also the roots that correspond to the first solution of Bethe equations, and I expand, I get perfect 0. Okay, this chop is again because numerically we don't get 0. We get 10 to the minus 146. Why 140? Why this kind of 140? Because we had precision 150, remember? So this is why these big numbers are coming from. We were solving Bethe equations with that precision. Okay? So we make chop, and then it's clearly difficult. And this is kind of very useful because, I mean, in practice, for example, you never ever know if S matrix is this or 1 over this. You never know what, actually, only Benjamin always knows the S matrix. I'm always amazed, but as he points out, I always write it wrongly in the talks. You never know if it's S or 1 over S. And of course, imagine I would have here 1 over S, and I would try the same thing, and I would just get a big mess. And then I would just fix here, run again, and okay, this is the correct sign. And in practice, this is how you do it. Okay, and you can check another solution. This was the first solution for 4. There is the third solution. You can check for 2. You can check a lot of things, and it all works. Okay, so this is the check of the spectrum. So let's now check that the norm of 2 Bethe states is given by what it should be given. The norm of a Bethe state. So let's compute the norm. So we take this state, and it's a big mess. It's even too big to show the output, but we can still be brave and ask to show the full output. So here is the state. So let's look for S of something. This is the state, blah, 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 blah. You say it's not the simplest thing you could imagine. And this is the coefficient of S004. It's this big mess here that starts here and ends here. Okay? And you have a similar mess for each of the elements of this wave function. It's kind of a complicated animal. So the first thing you do is you replace the root UA by one of the solutions to Bethe equations. So now it's already a little bit better. Okay? In order to see it better, we can put n, then here is what we will get. Okay? So you see that there is this numerical coefficient close to each case. Okay? Is it clear? How do we compute the norm of this guy? One way of doing it is just take this object, multiply it by the same thing where you complex conjugate. So a complex number a plus bi goes to a minus bi. Okay? So this took the object and multiplied by the complex conjugate. Then expand it. Now you get a big mess where you have product of 2 cats, but this is like scalar product of the cat 2, 1, 1, 0 with 4, 0, 0, 0. This is 0, unless the cats are the same. So what we want is to replace cat square by 1, and otherwise cat times cat by 0. Is it clear? Okay. So this is what is done here. So the first line is what we have here, and then we just take this last result. S of A times S of B goes to 0, but S of A squared goes to 1. And this is the number we get. We get 1257.3526, 00, okay? You might like this number or not. And then on the other hand, we have what we just said. We take Bethe equation, take derivative with respect to U1 up to US, replace after taking derivatives, replace u by Bethe roots, take determinants, and replace by this that just converts derivative in u to derivatives in p. Okay? And now you can run this Godin and ask, compute Godin, where for the set of roots, so this function likes a list of roots and the length. For the list of roots, put the solution to Bethe equation that we used above. And this is the number we get. Okay? And we can subtract both and see that they are exactly the same. And again, it's convenient. We could have forgotten factors, signs, and so on, and we see that it's perfect. Any question? Yes? No? It's clear? So let's go to the next check, which is maybe more interesting, where we take this brute force, and here I'm doing it just on a simple example. Apparently, I don't know why, but okay. Yeah, I don't know. So let's compute it again by brute force or by implementing this sum over partitions. So the brute force one is simpler. So suppose we take this state, this A44, let's replace it again by the Bethe roots. Okay. And now we want to make scalar products. So we construct this state, let me make. And now out of this state here, you see, is there a pointer? There was a pointer at some point, no? Out of this thing here, I can use this. Out of this thing here, suppose I want to consider this scalar product where this L is 2. Then what do I want to do? I want to, this guy keep, but this guy drop. It doesn't have vacuum in the last 2. This guy drop, this guy drop, this guy drop. Who do I keep? I keep this one, this drop, 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 keep this one, and so on. I keep the ones which have vacuum in the last 2 slots. Or I make scalar product. I just construct the object that I wanted. So this object here, you see, is exactly what I want. It's an homogeneous set of particles in the first 2 positions and zeros in the last 2. It's exactly what Feder asked me to write down here. Right? What this homogeneous gas means. And now what I do, I just multiply both states. I take one state, I multiply by the other. This is the product of the two states. I just expand and do the same thing. I expand and then do two cats go to 0 unless it's the cat square, which means it's the same, and then it goes to 1. And this is what we get. And here I do some absolute value. Is it important? Yes. Okay. So I'm computing the absolute value of this quantity. So let me define A as being the absolute value of this quantity. Okay, and this is what we get. So this is the brute force computation, 1.79 and so on. And now here, this is a slightly fancier example, where let's see what we have here. We have A, for a given length small l, this is the length of where we split the box in two, and again a list of Bethe roots. So the first thing we do is we have a block, which is like a pause, and we will define variables. We will say that S is the length of the list. And then this part here is clear, right? Is this part clear? So let's say with S equal to 4, computing this. This is just a simple product. Okay, there is no, forget about this error messages. And this is just this product here. Okay? So that part is trivial, just the part downstairs. And oh yeah. Okay. What about the part upstairs? The part upstairs I like more, I think it's funnier. So the part upstairs is the following. Let's say we want to split into two partitions. We have say 4, and I want to split this into two partitions. So what do? We do subsets of this, of partitions from either empty set up to length 4. So here are all possible elements, not the subsets, sorry, all subsets. The empty subset, 1, 2, 3, 4, the set with elements 1, 2, the set with elements 1, 4, and so on. And now what we want to do is to do a partition alpha and alpha bar. This can be alpha, for example, and alpha bar is the complement of this. Or this can be alpha bar, and then alpha is the complement of this. So if I apply the complement of 0 up to 4, if I apply this to each of these elements, let's see what we get. What happened? 4. I get, you see that, let's make a table form. And let's make here table form as well. And let's put one close to each other. You see that in the first line I got empty set, and then the complement is 1, 2, 3, 4. The second line I got 1, and the complement is 2, 3, 4, and so on. You see that 1 is just the complement of the other. So to generate a set of alpha and alpha bar, we just take these subsets, and then apply the function complement and identity to each of the elements. So this gives, so now if you have table form, oof. Okay, better not to. So this gives a set here where alpha is the full set, alpha bar is the empty set, alpha is 2, 3, 4, alpha bar is just 1, alpha is 1, 3, 4, alpha bar is just 2, and so on. So this gives all possible partitions into two groups. This is the hard part, you sum into two groups. Once you sum into two groups, now this sum over alpha, alpha 2 is alpha bar and alpha 1 is alpha. So we put alpha 2, you are summing over the elements of the second list. So you have U, in this case, for example, that is selected. Here it will be U2, U3, and U4. And here in the product, K would be U2, U3, and U4. But J would be just U1. Is it clear? Okay, good. So now, we can compute A of length 2 and list and the roots, say length 4, 4. What solution were we using? The third solution, okay, so third solution. And this is what we get. Okay, and this you see minus. It's very much the same. Yeah? Very good. So this is what is done here. Now, actually, it turns out that this you can do a little bit better. This statement is true for this, the fact that you take this wave function that we wrote there and make scalar product with this, it's equal to what I wrote even if the roots do not obey Bethe equations. So you can check without replacing the roots by anything. You can just compute them analytically and just leave the roots unfixed. Then it takes a little bit longer to evaluate, but it will also give 1, the ratio between the two. Okay? This is not true for the norm. It is not true that if I take any state of that form with any random P1, P2, P3, P4 and compute this norm, that it's given by this with just the same. It's crucial that they obey Bethe equations. But here, I take any state of that form and compute the scalar product, and it's given by this sum over partition. You don't need to obey Bethe equations. It's not important, but it's true. And there is a very nice determinant representation by Ivan Kostov. And here it is checked that this sum over partitions is nothing but this ratio of these two determinants here. And you see, okay, I can move it. The second one, the one is just what's called a van der Monk determinant, appears in matrix models. That is just product of ui minus uj over I smaller than j. And the first one is kind of a deformation of it. It's a very nice expression. Unfortunately, once again, as we will see later, we will have a prediction and a guess for how to deform the first expression at loop level, and it's not so obvious how to guess what the deformation of the second line could be if it exists at all. Okay. So, any question here? Any question about Mathematica? Any question about the physics?
So this determinant representation, how is it proved?
Yes, so the best would be let me remember. Yes. Yeah, it can be proved easily by starting with a Slavnov determinant and showing that this case is a particular case of Slavnov determinant. Okay? So it turns out that and Slavnov, I remind you that Slavnov determinant was the result between a scalar product of two beta states, one of them where the roots obey Bethe equations and the other one where they do not. And it turns out that with that is a general enough case that it includes this one as a sub-case. So by sending some of the parameters there to infinity, you do reproduce exactly this determinant here.
And the other formula?
Which one?
So
this one?
So also the other, yes, that one also you proved by other method. How do you check that these are the same?
Okay, the check that both are the same, we divide one by the other and see that it gives 1. But actually that's not the way we did it. So with Colby and Amit and Escobedo, we first proposed this expression for a scalar product in the so-called SU2 sector between a state and a vacuum. And we also found it experimentally. There we used algebraic bit ansatz. We wrote the state as a product of P operators and C operators, and we started commuting the operators to compute the scalar products, probably as you saw in the lectures of how to compute form factors. We commute the B's through the C's, stack through the hect of the vacuum, and when doing so, you generate easily a sum that then you recognize to be of this form. If you want, I can show it. I have a notebook ready, we can go through it if you want. Okay?
So it's semi-analytical.
It's a true statement that is, and then and then Omar Foda as derivations on showing that the two representations are the same. So in the end, all these ideas are checked. In the end, all these ideas are checked. Again, all these formulas are derived, but not at loop level. When we'll start having these contact terms and so on, then things will become a bit more interesting and more complicated, as we will see. Okay, is this clear what we are doing? So let me then try to now argue or write down right away. Let's now jump to the object that we are really interested in, which is this 3-point function. Okay? Now, which 3-point function? So let's let's be specific. Let's say we take this operator, the one which I'm erasing everything except it. Okay? So this is one of them. Let's call it OS. And let's put OS here. Let's say this is OS. So this is the operator. Let me use a yellow dot to indicate the derivatives. It can have one derivative here, two derivatives acting here, one derivative here. Sorry? Yeah, it's okay. Two derivatives here. And now let's suppose I want to consider the correlation function between this guy and two simpler objects that are BPS operators that are just, remember, this is Z, this is DZ, and so on. This will be just Z bars, almost just Z bars. Z bar, Z bar, Z bar, Z bar. Then I can just, at leading order in perturbation theory, we contract this stuff here. Another operator here that will have, again, Z bar, Z bar, Z bar, Z bar, 1, 2, 3, 4. And again, to leading order in perturbation theory, we just contract this stuff here. And here, let's fill this with some trivial, say, X field, which is another complex field. And here, some X bar field. And this is the correlation function we want to consider. BPS just means that you start with 6 Z's in this case and put these X's homogeneously in all possible positions. Then this is the analog of a descendant from the SU2 point of view. It is just the same as starting with Z to the L and just rotating a couple of X's. And then, at leading order, only this configuration will contribute. The X's by our charge need to contract with X bars, the Z bars need to contract with Z's. So out of the terms that constitute a BPS, only this one will contribute. The other ones, they don't contribute here. And now, what is this 3-point function a function of? So, let's see. We have this length, this is L. We have this length, let's call this L. And we have this length of this bridge, let's call this N. So this is a structure constant. This will be associated to a structure constant. So there will be some structure constant where one operator is non-trivial, is non-BPS, and the other two are BPS. We use this notation to indicate that. And this depends on L, L, N, and a set of beta roots UI. This is the object we are interested in. And the form of this 3-point function, of course, there is the usual space dependence. X1 minus X2 to some power, and so on. But that's not the end of the story, because this is an operator with spin. And when operators have spin, there is a slight difference. Here, there is some spin dependence. X minus 1, 2 divided by X. X1, 2 is just X1 minus X2. Minus the same thing with 3 to the power S. Okay? And, but that's just a kinematical factor. What we are interested is in this piece of data. In particular, note that if the external operators that we consider in our correlation function, when we wrote which we expand with these conformal blocks, if the external operators are simple BPS operators, which is our choice, we can do it. Then these objects here, in particular, will contain exactly this correlation function that we are interested in. So we can engineer the external states such that here in the middle, we will sum over these states with a given delta and this. Okay? So this introduces the object we want to study. So this is the analog of delta. It's also a function of the use. We want to study these objects, and I will start the next lecture by writing down a formula that relates this structure constant with these scalar products that we just defined and checked in Mathematica. And this will be sections, where are we? Why am I computer? Okay. So this will be here in our notebook. Let's close what we did already. And then we'll go to the structure constant section where we'll put these objects together. And then, most interesting, we will start going into the next part where we'll start checking this. And we have all these predictions and so on, and we'll start making contact between the world of the conformal bootstrap and so on, and four-point functions, and whatever we will predict based on this pin chain picture of the scalar products and so on. Okay, thank you.
So let's change it. Questions? Yes?
So this is of course all planar.
Yeah.
And if you have a 4-point function, there will be double trace operators that exchange.
Yes.
So
okay, so let me maybe develop a little bit more so that people understand. So, yes, if you consider two BPS operators as external operators, in the middle, it's not enough to sum over single traces. You have to sum over single traces and over double traces. This might be a bit counterintuitive. You might think that if you are only interested in the leading order at large n, summing over single traces should be enough, but unfortunately it's not the case. Because the contribution of double traces, the structure constant is enhanced and is favored as powers of n are concerned. So it is true that in the conformal bootstrap, you need to sum over double traces. However, if you choose this particular choice of BPS operators, the operators of lowest list are always single traces. Because what happens is that these x's and x bars, they need to be neutralized. And then you need the lowest state that contributes is the state z to the L. And then double traces would be... let me in the beginning of the next lecture comment on this double traces and do the power of n counting correctly, because I want to do it anyway. But it is related to the point, the reason why we chose to have this n here, and we could have decided let's put just no x's or x bars. It looks like they are spectators, they are doing nothing. It's precisely to avoid mixing with double traces. It's precisely such that we can go to perturbation theory and extract this information, and extract this data. I will make this clear in the beginning of the next lecture.